Okay, so this is the keynote for today, the Birnbaum lecture. We're delighted to have Michel Ledoux from Toulouse, who will tell us about optimal matching of Gaussian samples.
So thanks for the invitation and the introduction. It's a pleasure and an honor to be here. It's also a little bit embarrassing since what I will present is not really complete and up to what it should be for such an occasion. So that's about that's about optimal transport, optimal matching, which was already mentioned this morning in Yuval's talk, which is about the minimal transportation cost between two sets of points, which will be considered as random here. So mathematically, we have two independent samples, x and y, which are independent random points in RD. And we have a given cost function. And we try to find the best fit between xi, the coordinate xi, and another coordinate from the sample of the y's. And here we take, therefore, the infimum overall permutation of n objects, of n coordinates. And there is a 1 over n normalization here. And the cost function here will be nothing else as the Euclidean length in RD to some power p. So this problem about optimal matching will also be considered more or less equivalently as a transportation cost problem between some empirical measure and the reference measure. And it is actually in this form that we will discuss the problem later on. So here the interest is to try to find the order of this optimal matching in expectation. So it's a first order analysis. And as you can see, this question depends on a number of parameters. It actually turns out that the dimension d of the underlying RD space is quite important. It depends also on p, which is here the value of the cost function. And if you consider samples which are identically distributed, that this rate, this expected optimal matching, will of course also depend on the common distribution of the xi's and yi's. And in particular, there is a kind of model for this investigation, which is the case of xi and yi, which are uniform on the unit cube in RD. And in this case, the intuition is that the typical distance between n uniform points on the cube is typically of the order of 1 divided by n to the 1 over d. So it is expected that the optimal matching is given by this rate, 1 over n to the 1 over d, to the p if you have the p on the cost function. But this actually turns out not to be true. It's only true in high dimension when the dimension is bigger than 3, and we will try to discuss this a little bit. In particular, and this was mentioned this morning by Yuval, a major result on this question is the so-called Einstein-Komlos-Tushnady theorem from the 80s, which is stating that if you have independent random variables which are uniform on the unit square, then the optimal matching is actually given by an extra log n with respect to what was expected. So with respect to what Yuval discussed this morning, there is a normalization n, which is due to the fact that he was considering uniform distribution on the unit square with the length of the square was square root of n. So with respect to what is expected by the typical distance between uniform points on the square, there is an extra log here in this result. So here the notation, this equivalence notation means simply that the two quantities are within two constants, and the constant, of course, doesn't depend on n. And the proof of the theorem is typically of combinatorial nature, using dyadic partitions of the square and so and so. There has been a number of alternate proofs which were developed in the late 80s and early 90s by Shor, Layton, and Talagrand, using ideas from empirical processes and generic chaining. And actually, since then and until recently, not very much happened on this problem. And in particular, and this will be the topic of the talk here, we would be interested into this question for distributions which are different than the uniform. The uniform is a kind of model example. What happens if you have another distribution? In particular, what happens if you have a Gaussian distribution? And here this talk will focus on the Gaussian distribution in R2 and for the specific value p is equal to 2. So a very specific problem. Here is some motivation for this investigation. So this is a sentence from Poincaré, which may be roughly translated as: there are questions that should be asked, and there are questions that one is asking. And unfortunately, the incomplete result that I have to propose here is that if you have two samples of IID standard Gaussian in R2, then the optimal matching with p is equal to 2 is in between the rate of the uniform and the same with an extra log on the right hand side. And a possible conjecture is that the correct rate is the one on the left hand side, although I'm not really sure about that. So this is the goal here of what we would like to discuss. And before, let us present a few general facts and some surveys, some results on the general problem of optimal matching as presented here, in particular, depending on the various parameters which are here. Before doing this, we will kind of recast this optimal matching problem in terms of the so-called Kantorovich metrics. So if you take this cost here, which I recall is simply the Euclidean length in Rd to the p, it's a classical and easy exercise to see that if you take the two empirical measures on the samples xi and yi's, then this quantity, which is defining the optimal matching, is nothing else as a so-called Kantorovich metric, Wp to the p, between the two empirical measures. This is simply a consequence of Birkhoff theorem describing the extremal points, the extremal measures of bistochastic matrices as permutation matrices. And this Wp, or Wp to the p, is the Kantorovich metric. So the Kantorovich metric between two probability measures mu and nu is defined as this infimum of the integral of the cost, this cost Cxy, with respect to all probability measures on the product space with respective marginals mu and nu. So here, respective marginals mu n and nu n. And if we now just rephrase the optimal matching question we would like to investigate, is to try to find the order of growth of this quantity between two independent samples, xi and yi. This is just a rephrasing in terms of this Kantorovich metric. And by very simple means, using kind of Jensen's inequality and independence, if you assume that the xi's and the yi's are IID with the same common distribution mu, it is more or less equivalent to ask for the size of the cost of the Kantorovich metric to the p from the empirical to the reference measure mu. This is the measure common distribution of the xi's. And it is in this form that we will actually discuss this optimal matching problem. You have...
When you say it's equivalent, it's clearly equivalent when you don't care about the exact constant. But when
yeah, up to constants.
Yeah.
Up to constants. It's equivalent up to constants. So this is in the form that we will discuss here. We have a sample x1 to xn of IID random variable in RD, and we look at the empirical measure, and then we discuss the size of the Kantorovich metric from the empirical to the uniform. So this is the picture, and as we mentioned before, there are some parameters entering the discussion, and these are the three main parameters: the dimension d, which will turn out to be very important, the value of p in the definition of the Kantorovich metric, and for simplicity, we will mainly concentrate on p is equal to 1 and p is equal to 2, and let us mention that W1 is always less than W2, so we have this comparison. And then the last parameter is the underlying distribution, and as announced, we will be interested into the case where mu is Gaussian.
Because your WP is already has the normalization.
There is already a P here, so something like this should be okay. Okay. So we'll basically consider what is called, or what are called, the standard rates, namely that we will try to compare this quantity, at least find upper bounds on this quantity with respect to the known uniform example that we presented before, and that we will recall also before. There are some other unusual or stronger rates which may occur, in particular in high dimension and when the underlying distribution is not very regular, but we will not discuss this. We will be considered only with the standard rates, namely comparison with what is known for the uniform. So before entering the discussion, this is just a slide about the terminology. We are using Kantorovich rather than Wasserstein, following an essay by Verschik. And as you can see, Wasserstein is a mathematician working algebraic K-theory and algebra and analysis, and he is not guilty of the distortion of terminology between Wasserstein and Kantorovich. Just for the anecdote, in the 42 paper of Kantorovich, where he is introducing those metrics, he is using for those metrics the letter W. So this is the discussion that we would like now to outline via those parameters. And as already mentioned, dimension turns out to be quite important. So let us start with a very simple case, which is namely the one-dimensional case, in which case there are some very specific representations of the Kantorovich metrics. A very famous one and classical is a representation of W1 in terms of the distribution functions of the probability measures nu and mu. When p is bigger than 1, you can use the inverse or generalized inverse of the distribution functions to get this type of description of the Kantorovich metrics. And in particular, using this, it's not very difficult. This is a very first result, namely that for any distribution mu on the real line, you get the standard rate. This is the rate of the uniform as soon as you have this type of integrability on the distribution. So this is satisfied as soon as you have slightly better than a second moment and you have this property. So this is rather general, W1, as soon as you have some moments bigger than 2, then you get the standard rate. Another tool which is used in dimension 1 are the so-called order statistics. This is another very classical and easy fact, namely that if you recall the two empirical measures on the samples xi and yi, as we have seen, the Kantorovich metric is the size of the optimal matching, and on the real line, it's easy to see that this optimal matching is achieved in this way, taking the two order statistics of the samples. And with this, and again, using some independence and Jensen's inequality, what you get for the rate, the Kantorovich metric between mu and mu, is basically this quantity, namely the average of the expectations of the order statistics, of the piece moments of the order statistics suitably resetted. So let us test this formula on an example. You take the uniform distribution on the unit interval. It's easy to see that the ith order statistics follows a beta distribution, and with this you just compute and you get the rate. And the rate is not 1 divided by n to the p, as was the intuition, but n to the p over 2. When p is equal to 2, you can actually do a very precise computation. So the expected rate of W2 is 6 over n, and for the bipartite case, when you have two independent samples, mu n and mu n, you get this quantity. So W2, the standard rate is of the order 1 over n. What happens for other distributions? So suppose you have a distribution mu on the real line. Assume that it has a density, although this is not strictly necessary. Then you get the standard rate. So this is the rate of the uniform case, if and only if this condition is now satisfied. So you have this expression that involves the distribution function and the density. So for the matter of comparison, for the W1, we had only this condition, which is satisfied as soon as you have some moments, bigger than 2. And for W2, you have this expression that involves a kind of comparison between the distribution and the density. And after a little bit of change of variables, you may rewrite this expression in this form here. And this function I of t is this composition between the density and the inverse distribution f minus 1, which sometimes is called the isoperimetric profile of the distribution mu. So you see that the picture is a bit different than for W1. And this result actually is of particular interest for a specific class of distribution on the real line, namely log-concave distribution. So these are distributions on the real line with density, say, exponential minus v, and v is convex, right? And this equivalence for the class of log-concave distribution can actually be made a little bit more precise. And what you actually can prove when mu is log-concave is that you have accurate two-sided bounds for the W2 metric between mu and mu, given in terms of this integral here that you evaluate between those two endpoints of this interval. So I briefly flash here the technical arguments which are behind and which are actually not difficult but not so easy. One has really to be a little bit careful. One important point is that if you start with independent independent IID random variables with a common log-concave distribution, the xi star, the ith term into the order statistics is also log-concave, has also a log-concave distribution, which is coming from this expression here. And once you have a log-concave distribution, it's possible to do careful computation on the variance, and you end up with this formula. So let us test this those two-sided bounds on some specific example, Gaussian, because this is the topic of the talk. Then it's known that this I function is of this order as t goes to 0. And what you get with respect to the standard rate is a log-log. So that's the first surprise. With respect to the 1 over n of the uniform case, you get this log-log. Another example is for the exponential, you get a log. And there are other things, and this has been discussed in some joint work with Sergei Bobkov. So I don't have a picture of Sergei, but he's not so young either, so I think it's fair. So actually this discussion was presented here for W2, but it can be made exactly similarly for WP. And if we now summarize the picture for the one-dimensional Gaussian, we have the following. Just to recall, for the uniform distribution, the rate is 1 divided by n to the p over 2. And the picture for the standard normal is that we get the same thing for p less than 2, and then there is a change, log log n divided by n, and then it's even worse when p is bigger than 2. So W2 is much more sensible to distribution than W1.
Do you mean sensitive?
Sensitive. Thank you. Thank you.
Maybe it's also more sensible.
Well, I don't know. Okay. So this was for dimension 1. So let us skip to higher dimension, and let us, for the moment, go to d bigger than 3. So these are the results for the uniform. Dimension 1, we have 1 over n. Dimension 2, this is the Einstein-Komlov-Chusnadi theorem log n divided by n. And when d is bigger than 3, we actually get the expected rate, which was kind of intuitive from the fact that n uniform points on the cube should be of the order distance should be 1 divided by n to the 1 over d, and here we have a square because of this square. Okay. So things are easier in dimension 3, and this is a sentence from Talleyrand, although I'm not really sure to fully understand it, but here it is. So things are easier in higher dimension, and in particular, it was possible during the last years to attack this question of extending this type of rate for more general distribution than the uniform. And this has been investigated in a number of papers. These are the authors, showing that if you have distribution on RD, when d is bigger than 3, with enough moments, using dyadic partitions, more or less like AKT, you are able to show things of this type. So let me start with the end. When d is bigger than 5, you have the correct rate. So this is pretty general. As soon as you have enough moments on your distribution, you have the correct rate. When d is equal to 4, besides of this log, it is also optimal. 2 divided by 4 is a half. But it's very bad for the small dimensions, because for the small dimensions, it should be 1 over n or something of this type, and it's only 1 over root n. So the general methods are not very useful in this case for the matching. Now, even more refined results in dimension 3, it's possible sometimes to show that some limit exists. Also, the values of the limit are not known. They follow from kind of subadditivity arguments. And these are the type of results that you can get in higher dimension. So d is equal to 1 was very specific due to the representations of the Kantorovich matrix. In higher dimension, you have more space. It's easier also in a sense. And now we come to the question of dimension 2, and in particular this AKT theorem that I recall here, which for W2 expresses that you get log n divided by n. If we apply, as we just mentioned it, the general bounds discussed before, you only get a 1 over root n, which is not very satisfactory. And this has to be compared, this rate here has to be compared with the case of W1, where again W1 is easier, and it was proved already a long time ago that as soon as you have something just bigger than the first moment, you have the correct rate for W1. So again, W1 is easier than W2. So the purpose here is to try to understand this question for more general distributions in dimension 2, and our main target will be simply the Gaussian distribution. And in order to investigate this question, we will relate on a recent result that Yuval already mentioned this morning, which is due to Ambrosia, Stra, and Trevisan, who actually not only reproved the AKT theorem, but found the exact limit, 1 over 4 pi. In the bipartite case, which is the optimal matching between two independent samples, xi and yi, you get 1 over 2 pi. And the methodology was based on a PD ansatz by physicists, as already mentioned this morning. So the exact limit here. And not only the uniform on the unique square, but more generally, each time you consider the normalized Riemannian volume element on a compact Riemannian manifold of dimension 2, you get the same answer. Okay. And this morning, Yuval told us about the 2 spheres, the 2 torus, and here you get the exact limit in this more general setting. So we will try to use a little bit of the methodology, the machinery, which is behind this very nice result. And let me just briefly indicate the steps which are used in this investigation. And I will not discuss the question about taking the limit, but let me just describe the steps in order to find the correct upper bound using this PDE mass transportation methodology. So there are 2 main steps. First step is a regularization procedure, and the second step is a kind of energy estimate using the heat kernel, or actually the trace of the heat kernel. So let us briefly discuss this. And this discussion can actually be made in any dimension. So let us consider a compact Riemannian manifold. Mu is the normalized volume element on the manifold. And we look at any dimension here. For the discussion, this will not be important at this point. So 2 steps. First step is this regularization, which is simply the following. We just regularize the Dirac measure by the heat kernel. So we replace the empirical measure on the sample by this measure, which has a density which is given by the heat kernel on your manifold. Okay? So this is a way to smooth out the Dirac mass around Xi. And of course, if you do this replacement, there is a price to pay. And using standard convexity of W2, you can actually show, this is very easy, that what is the price to pay to change the empirical measure into this smoothed measure mu nt is given by this contribution, which is called the dispersion contribution, which is simply the integral of the heat kernel in the 2 variables. So that's not very difficult. So what is the advantage of this regularization procedure is that now you are dealing with a probability that has a density with respect to the underlying measure mu. Okay? Density given by the heat kernel, so it's a random density depending on the sample. And the heuristic is the following. This density here, call it F, is just 1 over n, a sum of, for each fixed y, this is a sum of IID random variables. So you have a kind of central limit theorem phenomenon. Since this is a heat kernel, the mean is 1. And then you have 1 over n, 1 over square root n, a Gaussian by the central limit theorem. Okay. So the picture is that you have mu nt, which has a density with respect to the underlying measure mu, and this density is of the type 1 plus something small, 1 plus epsilon. Okay? And now there is something very classical in optimal transport, in the study of the Wasserstein metric, is that if you look at the infinitesimals here, namely if you have a density which is 1 plus epsilon g, then the W2 behaves like this quantity.
Sorry, Michel, what t are you taking here?
Excuse me?
What value of time are you taking?
At this point, it's fixed. At this point, it's fixed. After, we will have to optimize. But here, the discussion is for fixed t. Okay? So the heuristic here is that we have a density which is of the form 1 plus epsilon something. And this 1 plus epsilon, in terms of the W2, this converges to this quantity. So here, delta is a Laplace operator on your manifold. You take the inverse, apply it to G, which is this density, assumed to be smooth, and you take the L2 norm of the gradient. Okay? So we'll discuss this quantity. This quantity is actually what is called a dual Sobolev norm.
There's something very unintuitive here because you're trying to match to this empirical discrete measure, and you're saying it's close to this other measure which has a density almost near 1.
Yeah. But that's the way they are doing it. So this is the dual Sobolev norm. And behind this limit here, there is actually an inequality, which is the following. Each time you have a measure which has a density f with respect to mu, the Wasserstein Kantorovich, I'm really sorry. The Kantorovich W2 between the two measures is actually upper bounded by this dual Sobolev norm.
Should assume that Vershik is watching the recording.
Yeah. And others. So, let me briefly sketch the proof. The proof is based on a very classical Kantorovich duality, describing the W2 as the supremum between the integral of q phi with respect to one of the measures and the integral of phi d mu with respect to the other. And the q or q1 or qu here is just what is called the infimum convolution with the quadratic cost. D is the Riemannian distance on your manifold. So you take the infimum convolution with respect to the quadratic cost. This is the Hopf-Flachs formula that satisfies the Hamilton-Jacobi equation. Namely, this is a semigroup, and if you take the derivative, you get this nonlinear minus a half of the gradient squared. So once you have this very classical representation in terms of this infimum convolution semigroup, the argument that I'll not discuss in detail here is just an interpolation, a suitable interpolation between those two quantities. You interpolate along some increasing map U. When you take the derivative of this, you get this contribution by the Hamilton-Jacobi equation. And on the other piece, you force the introduction of the delta inverse by integration by parts, and you get it.
Can you just comment why it was chosen the representation as a supremum? Usually it's over Lipschitz function.
This is for W1, but this is W2.
Okay, good, thanks.
So indeed, the Kantorovich duality for W1 is a sup of this over one Lipschitz function, but this is W2, which makes a difference actually. So this is the argument, which is an interpolation argument, which allows for the proof of this inequality. So this actually also works for WP. We'll not discuss this here. One interesting point about W2 is that you can make more explicit this dual Sobolev norm in the following sense. Formally, the inverse of the Laplacian is given by the integral of the semigroup, of the heat semigroup PT. And just using some integration by parts, you can simply rewrite this dual Sobolev norm as a trace of the semigroup. Namely that you integrate PSG, G is f minus 1 as before, G is f minus 1 as before. You integrate PSG, you take the integral of PSG with respect to mu, and then you integrate in time. So this is just, since you are in L2, you just use integration by parts and so, and you end up with this. So the conclusion is that you are able to bound the Kantorovich metric W2 by this quantity. And now you may come back to this central limit theorem heuristic. Namely, this G is f minus 1, and f is this density coming from the regularization procedure, the sum of the heat kernels. And the central limit theorem here, we just use it in the form of the computation of a variance. Because at some point we have to take here the expectation of the W2. If we take the expectation of W2, we will eventually take the expectation of this by Fubini, and we take the expectation of this. And if you take the expectation of this, so first of all there is a shift of t plus s, because you are applying ps, and then you are simply dealing with a sum of independent IID centered random variable. You take the variance, and you get 1 over n, the expectation, the variance of one of them. Okay? And x1 has distribution mu. So if you integrate this with respect to the invariant measure of your heat kernel, your heat semigroup, you end up with this. And now, finally, you have to integrate from 0 to infinity, and you get a trace estimate on...
You get a change of the time, so 20 plus s.
Yeah, I change here from t, so it was from 0 to infinity, but it was t plus s, so it becomes from t to infinity ps.
No, in that sense, in this formula, you went from pt plus s from mu to y to y, so don't you need to double the time when you do that?
Maybe, yeah, you're correct. Maybe there is a 2 times
There's a hidden 2 there.
Yeah, maybe there is a 2 time. Yeah. Thank you. Yeah, should be a 2t here. Thank you. So, summary of the discussion up to the factor 2. We were able to control this expectation of W2 in terms of the dispersion, which is coming from the regularization property, and this second term here, which is upper bounded by this trace formula in terms of the heat kernel. Okay? So that's another way to write the result. And now we have to optimize in T, because this was done for every fixed T, and now we optimize in T. And if you are on a compact Riemannian manifold with dimension D, it's not very difficult to see that the dispersion is of the order of T. And to evaluate the trace here, you simply use heat kernel bounds. And actually, it is enough to deal with the small time heat kernel bounds. And on a compact manifold of dimension D, the heat kernel bounds are of this order. Now you optimize, and you get this. So that I repeat here. So when D is equal to 1, you get the standard rate, 1 over n. When D is equal to 2, you get the AKT theorem, log n divided by n. And when D is bigger than 3, you get the rate that we discussed, standard rate 1 over n to the 2 over t.
But again, this is duality, so there's no explicit matching.
There is no explicit matching. This is duality, upper bounds. But what is interesting is that the heat kernel bounds actually exactly reflect the rates.
So if instead of heat kernel bound you use entropy bounds, they will give you much worse.
Probably, yeah. And actually, this was discussed for W2, and you can do it for WP. This is more or less known in the literature, although not for all possible values of P and D. And if you do it here, you get everything. So to get to the limit, it's a further step. You have to work more, right? You need more specific, more precise arguments in order to reach the limit. And this is done in this Ambrosia, Stra, Trevisan paper. But they only do it in this very particular case, P is equal to 2 in dimension 2. And outside this particular case, the limit is not known. And in particular, one very simple, one interesting example would be W1. But this is the question of the limit for W1 is open. So let us start the talk, because we have to say something on the Gaussian. This was in the title. So what's the picture about independent standard Gaussian? So in R2, what is the order of this quantity? And we aim at studying this question using the approach we just described, this PDE mass transportation approach that we described. So let me just briefly mention that the issue about lower bounds is actually rather easy, because the picture is that if you have a Gaussian, you can always contract it by a Lipschitz mat to the uniform. So the lower bounds for the rates for the Gaussian will always be bigger than the one for the uniform. So you get lower bounds by a very simple comparison with the uniform. So the issue here is to try to understand upper bounds. And if we apply this PDE methodology, we can just, start from the very general formula that we had between dispersion here and this trace formula, which applies for more general kernels than on a compact Riemannian manifold. And it applies here in the Gaussian case, but you have to replace PS by the Mailer kernel of the Gaussian distribution, which is here. So one good thing about the Mailer kernel is that when t is small, you get the t to the d over 2, which was the uniform bound that we used in order to show the results for the uniform distribution. So this is the good portion of the Mailer kernel, and the less good portion is this one, because of course it depends on where you are. It depends on the parameters where x and y are, and if they are too far or too close in a sense, there is nothing uniform that you can expect on the Mailer kernel. Okay. So in particular, if you do it directly, you show that the dispersion is very easy. It is of the order of t, as it was the case before. The trace is of this order. Due to the explicit representation of the Mailer kernel, you get a trace which is of this thing. But here things are starting to get bad, because this is of the order of s to the d when s is small. And if you do the optimization, you get this. So 1 divided by n to the 1 over d. So in particular, if d is 2, this is 1 over root n. This is far from what we expect and not satisfactory. So we have to go further with respect to what was done before. And the further step is a localization procedure, namely that instead of looking at the Gaussian measure on the whole of RD, you try to localize it on a big ball. Well, not so big ball, actually. A ball of radius square root of log n. And you do a very simple coupling to replace the empirical measure on your sample of Gaussian variables by the empirical measure on a sample of the Gaussian restricted to the ball. So the advantage here, I'm skipping several details here, is that the trace is of this order, so it is exactly of what is expected, times something that depends on the size of the ball, which is of the order of square root of log n. And if you combine everything, so this PDE methodology described before, together with this localization argument, the conclusion is the following. So the good news is that the methodology, this PDE methodology, is good enough to recover the one-dimensional case. You get the log n divided by n in dimension 1. But when d is bigger than 3, we know that by general facts, it should be 1 divided by n to the 2 over t, so there is an extra factor log n. So it's good enough to cover d is equal to 1, but presumably there is an unnecessary extra factor log n, which is showing up here, and probably also here. Okay. So this is what we have obtained. We have squeezed the rate between log n divided by n and log n squared divided by n. Due to the preceding comment, probably it could be this one. And there is a simulation by Stra, which is saying that it should be 1 over 5. So I don't know what 5 has to do with the Gaussian distribution. It's not so close from 2 pi. And maybe there is some log n somewhere. So let me conclude by saying that you can develop the same methodology for all p's between 1 and 2, p strictly less than 2, and you get the optimal rates which are the same as for the uniform. So when p is equal to 1 was known by this Talagrand-Yukic thing that we mentioned before, and you can push until 2, just below 2. It will be the same as uniform. And then the question is what happens at p is equal to 2. So I'm sorry, not able to not being able to answer this question. And I would like to thank you for your attention.
Okay, what's that wall?
You have to go there, and you'll see it.
Did you write that?
Guess it, yeah.
To what extent was this project really based on or dependent very much on the Gaussian nature of the distribution?
Because you have to compute the trace, right? You have to say something on this thing here. So, if you have heat kernel bounds as we did before, then you can do it. But this is the case. But I agree that it's possible to do. Yeah.
Is there some distributional result? You're doing the mean. Is there a central limit theorem?
There are central limit theorem. When you recenter, there is a central limit theorem. This is a recent paper by Del Barrio and Lubes. And they are proving a central limit theorem for W2, or probably also WP, but W2 square minus its expectation. This goes to a Gaussian. But this doesn't say anything about the order of this. On the other hand, you can also use standard concentration inequalities to get some informations on the distribution of W2. Because it's concentrated as Gaussians, actually, it has Gaussian concentration, so you can say something on the tails of W2 once you have the size of this expression.
You said that the PD approach also works for P between 1 and 2. What is the equivalent of the Sobolev norm that you get in this case?
Well, each time you see 2, you replace it by P. But you don't have representations in terms of traces. So this is why here you have to work a little bit.
But you have the same operator that shows.
Yeah.
So, if you can go a little bit to the slide where you showed the variance.
With the 2T?
No, just the inequality with the 4 times the green.
This one?
No, yeah, this one. Yeah, exactly this one. So this is an incredibly appealing formula that on the first line there,
Yeah.
which is this is a duality proof
Yeah.
of that. But right, but we'd like to say that a specific allocation will give us a
This proof doesn't give anything in this respect. In the Ambrosia Stra Trevisan paper, they have something. They have a little bit of something, but not.
Yeah, not enough. But this is very appealing to just nail down if some variant of this gradient flows.
Does this PD approach also give lower bounds?
Also gives.
Lower bound?
Yeah, but you have to work more. But here, since we are concerned with the Gaussian, we do not discuss lower bounds. There is a way to, using the PDE approach described by Ambrosia, Stra and Trevisan, it's possible to reprove the AKT theorem. I mean, the lower bound part of the AKT theorem.
But in a sharp form, they get the constant also in the lower.
Yeah. And they get it for W1 also. They really proved the lower bound for W1.
That paper is not for the faint of heart. Any other questions or comments? let's thank Michel again.